This line introduces the feature matrix X, a numerical array representing the data to be preprocessed. It's a 3x3 matrix, meaning 3 data samples with 3 features each. Think of each row as a different sample or data point, and each column as a different feature or characteristic of that sample. Let's dive deeper into it. This line shows the actual numerical values in the feature matrix X using NumPy's array representation. The numbers represent the values of the features for each sample. For example, the first sample has feature values of 1, 2, and 3. Let's see how this matrix gets transformed. This line shows the application of scikit-learn's "normalize" function to matrix X. The "norm" equals L2, argument specifies that L2, Euclidean, normalization should be applied to each row. This process scales each row, sample, so that its Euclidean norm, length, is equal to 1. This line introduces the variable that will hold the result of applying the "normalize" function. After the normalization, x_norm will contain the transformed matrix. This is the key output of our transformation. This indicates that what follows is a multiple-choice question testing your understanding of the effects of the L2 normalization. This sets up the core question, to evaluate the properties of the normalized matrix. You need to consider how each of the following choices applies to the normalized matrix. This option checks if the L2 norm, the square root of the sum of squared elements, of each row in the transformed matrix is equal to 1, a defining characteristic of L2 normalization. This statement checks if the sum of the squares of elements in each row of the transformed matrix is greater than 1. Recall that the square of the L2 norm is equal to the sum of squares. This option tests if the largest absolute value within each row is less than or equal to 1 after normalization. This option asks whether the ratios between features within a single sample are altered by the normalization process. This shows the initial data, a 3x3 matrix representing 3 samples with 3 features each. Each number represents the value of a feature for a specific sample. For example, the first sample has features with values 1, 2, and 3. This line indicates that we are using a function from the scikit-learn library in Python. The function "normalize" is used for preprocessing data. Specifically, it's being used here with the "L2" norm, also known as the Euclidean norm, which is a way of measuring the length or magnitude of a vector. This represents the result of applying the "normalize" function to the input matrix X. The values in x_norm will be different from x as the function scales each row, each sample, to have a length, Euclidean norm, of 1. This is the core of the quiz question, asking the learner to determine which statements about the resulting normalized matrix x_norm are correct. It tests understanding of what L2 normalization does to the data. This option checks if the length of each row, sample, in x_norm is equal to 1 after applying the L2 normalization. The L2 norm is calculated as the square root of the sum of the squares of the elements in a row. This option tests understanding of the relationship between L2 normalization and the sum of squares of elements in a row. If each row has a norm of 1, what is the value of the sum of squares of its elements? This option examines the effect of normalization on the range of values in each row. Does L2 normalization guarantee that the largest value in each row will be less than or equal to 1? This option probes understanding of how L2 normalization affects the relative magnitudes of features within a single sample. Does this type of normalization preserve or change the ratios between features in a given sample? This is the anticipated location of the answer to the multiple-choice question, identifying which statements A through D are true. Hey there, this is our feature matrix. Think of it as a table where each row represents a data point, like a person or an object, and each column represents a different feature, like height, weight, or age. For instance, the first data point has values 1, 2, and 3 for the 3 features. This line defines the input feature matrix X as a NumPy array. This is a crucial piece of data to understand what the normalization function will modify. This is our starting point, VOMC. It's a 3x3 matrix representing our features. Each row is a data point, and each column is a feature. We'll be applying a normalization technique to this data, which will change how the rows are represented, but not the underlying meaning of each row. Here's where the action happens. We're using scikit-learn, a popular Python library for machine learning, and its normalize function. Specifically, we're using the L2 norm, also known as the Euclidean norm. This function will transform each row of the input matrix X by scaling it so the Euclidean length, or distance from origin, of each row becomes 1. This is our quiz, VOMC. We've applied the L2 normalization and now we need to understand the properties of the resulting matrix. Are you ready to test your understanding of what L2 normalization does to the data? The multiple choice questions test your understanding of the impact of L2 normalization on the data. We will check the validity of each statement with the properties of the normalized matrix. This is what we want to understand. What are the properties of this normalized matrix after applying the L2 norm? The quiz questions will explore whether the L2 norm of each row is 1. If the sum of the squares is still 1, etc. This normalized matrix is created by applying the L2 norm to each row of X. This line indicates that we're using the scikit-learn library's normalize function with the L2 norm to scale each row in our data matrix X. The L2 norm, also called the Euclidean norm, is a measure of a vector's length. We are essentially normalizing each row, representing a data point, to have a length of 1. This process doesn't change the relative values within each row, just the total magnitude of each vector. This is the name we'll give to the resulting matrix after applying the normalize function. Each row in this new matrix, XNORM, will have been rescaled to unit length, length 1. This is the result of the L2 normalization. This statement checks if after applying L2 normalization, the Euclidean norm, the square root of the sum of the squares of the elements in a row, of each row in the transformed matrix XNORM is equal to 1. This should be true, as this is the definition of L2 normalization. This statement tests if the sum of the squares of the elements in each row of the normalized matrix XNORM is greater than 1. Since L2 normalization scales each row to have a Euclidean norm of 1, the sum of squares is 1, 1 squared is 1, not greater than 1. This statement questions whether the largest absolute value, without considering its sign, within any row of XNORM is less than or equal to 1. Because L2 normalization scales each row down to unit length, the largest value in each row must be less than or equal to 1. This line introduces the feature matrix X, a crucial component of the machine learning problem. It's a 3x3 array of numbers that represent the features of 3 different data points. Understanding this matrix is key to understanding the normalization process. This line explicitly defines the feature matrix X. Each row represents a data point, and each column represents a feature. For example, the first data point has features 1, 2, and 3. Let's see how this data is transformed. This phrase sets the stage for the core concept, the mathematical method used to preprocess X. It tells us we're going to use L2 normalization, which is a common technique in machine learning. The first step of the L2 normalization process. For each row, data point, in X, we compute its L2 norm, Euclidean norm. This is found by squaring each element in the row, summing the squares, and then taking the square root of the sum. The second step is to scale each row. Each element in a row is divided by the L2 norm calculated in the previous step. This process ensures that the length, L2 norm, of each row becomes 1. This is what we get after applying steps 1 and 2. It's the transformed version of the matrix X, where each row is now a unit vector, length 1. This is a key property of the L2 normalized matrix X_norm. Because of the normalization, the L2 norm, length, of each row will always equal 1.